Hello my friends, so welcome to lecture number 2 of Chemical Kinetics lecture series. So today we would continue our discussion on integrated rate laws. So in this lecture today we will try to derive the rate laws in integrated form in terms of the appearance of the product. Okay, so let me tell you, so far we have been studying reactions in this form. A reactant going to give you product P, but what we have done essentially in the last lecture, that we have studied the rate of disappearance of the reactant. So that means, so we have studied something like this: minus dA dt is equal to Ka to the power n. Okay, so this is in terms of the disappearance of the reactant. So here today what we are going to follow is to express the chemical kinetics in terms of the appearance of the product. That means here we can't use the minus sign anymore because it is the rate of the appearance of the product. So dp dt is K multiplied by P to the power n. Okay, so we are going to follow, or we are going to form the integrated rate law of the first order chemical kinetics in terms of the appearance of the product. So what we do here is we follow simple steps. So the simple steps are, that is, we assume that at t time t is equal to 0, okay, the initial concentration of product, the reactant A was the smaller case A, and the concentration of the product is 0 because no product was formed. Now at time t is equal to t, so x amount of product is formed, let's assume. So at that time point, the concentration left for the reactant is A minus X. Okay, so this is the concentration of the product X, and this is the concentration of the product P is X, and concentration of the reactant A is A minus X at any time t. So therefore we can express that the rate of the reaction is equal to the rate of the formation of the product P is equal to, we can write dx dt is equal to, since we have already assumed that this is the first order, so rate constant multiplied by A minus X to the power 1. Okay, so here order is 1. So therefore, like the last time, we have to integrate this equation. So therefore dx over K multiplied by A minus X is equal to dt. Okay, and of course we integrate that here with some constant of integration, that is the z. Okay, so or we write here minus, okay, so this sorry, we can put the k over here. Okay, right. So therefore we now come to this equation. There is minus natural log of A minus X is equal to kt plus z. So z is the constant of integration. So now we are going to find out the value of z. So to find the value of z, we can put that at time t is equal to 0, okay, or x was is equal to 0. So here in this equation, if you put t is equal to 0, okay, so z comes out to be, hence, so therefore we get z is equal to minus natural log of a. So once we get that z is equal to minus natural log of a, so therefore we can we can rewrite this equation once again. So we can write it here, or so we can directly write kt is equal to natural log of a divided by a minus x. So this equation is actually the integrated rate law of first order equation, where we can relate the time t with the concentration of X, okay, in the chemical reaction. So if we know one of the values, means we have started the reaction, so the initial concentration A is known to us. So if we know the rate constant, we can easily find out the value of X at any time t, and vice versa. Okay, and if we know the time t and also the X, provided the A is known, we can also find out the kt, or we can also find out the rate constant K. All right, so the same equation can be written like that, so in the form of X. So I'm going to clear this part, and you can write that X is equal to 1 minus, sorry, we can write X is equal to A multiplied by 1 minus e to the power minus kt. Okay, so that is an alternate form of the expression of the same thing. Okay, so this is one of the most common way to represent the first order reaction. And remember, in the last lecture we have expressed the integrated rate laws in terms of the disappearance of the reactant. So now it is in terms of the appearance of the product X. So therefore we are now going to look that what are the applications of the first order integrated rate law. So I'm going to clean the board and we'll discuss two examples of the first order rate law. Okay, so the first order kinetics, as I said earlier, that can be applied into two practical examples. So one is the radioactive decay. So for example, I can write one radioactive reactions. In fact, there are many radioactive decay reactions. So for just an example, I am writing this one. So copper 64, this is a radioactive isotope of copper, is going into zinc 64 plus releasing of a beta particle. So here the rate of decay can be expressed as minus dn over n, or dn dt, sorry, minus dn dt. Here the uppercase N stands for the number of radioactive particles or radioactive atoms present at any time t. So this is equal to some constant lambda multiplied by the n. Okay, n means the number of radioactive, okay, that I already explained, radioactive atoms already present. So this looks pretty familiar of our first order chemical kinetic equation when we represented the equation in terms of the rate of disappearance of the product. So, or we can readily transform this equation into an expression something like this: n is equal to n naught multiplied by e to the power minus lambda t. Okay, or the same thing, we can express n over n0 or n naught is equal to e to the power minus lambda t. So here lambda is called the decay constant. Okay, so the decay constant lambda is related with the half-life of the decay. So this is denoted as 0.693. So this is the expression from the half-life we are taking, is equal to t half. So we have already found out for the first order kinetics that the half-life of first order kinetics is 0.693 divided by the rate constant. So here the decay constant takes up the form like this. For this particular reaction, the t half can be expressed as 12.8 hours. Okay, so if we take t half is equal to 12.8 hours, and we can easily calculate the value of lambda, the decay constant, and from that either we can calculate how many number of particles are left after a certain time t, or what was the total amount of radioactive atoms or radioactive particles or total amount of radioactive materials, that is basically a naught. It could be easily found out. So therefore this kind of examples and this particular equation is of our interest, because in tests and exam certain numerical problems may come from these problems. Okay, so now we go to our next example. Our next example that where the first order kinetics can be applied is the bacterial growth. So from few bacteria, a lot of bacteria, means a colony of bacteria is grown. So if we try to represent the growth of the bacteria from this graph plot, so this x-axis represents time and the y-axis represents the number of bacteria cells basically. So it starts with n naught, certain small number of bacteria. So with time t, one can observe that the growth, that means the number of bacteria, that means the new cells that are being born, they follow something like that, an exponential pattern. So the same kind of the change actually can be mathematically represented by like this, that is the change of the number of the bacteria d and dt is equal to lambda g multiplied by the time t. Okay, so sorry, uh, where is my duster? Okay, so actually let's represent it like this. So dn over n is equal to lambda g dt. Yeah, so we can represent it like this, or we can write dn dt is equal to lambda g n. Yes, so n is the number of bacteria that is present at any time t, and lambda g is called the growth constant. So in earlier case we represented lambda as the decay constant, but it is just the opposite, so it is called the growth constant. So therefore from this equation, if we integrate it, so we can easily write n is equal to n naught e to the power lambda g multiplied by t. So you just notice that everything here is positive. So here we don't have a negative sign here because it represents the growth. So now how to find the lambda g? So lambda g, once again, it should be related with something like 0.693 or natural log of 2 divided by, so here we can't use the word t half-life, because half-life is applied to the change where it is decaying or decreasing, but here it is increasing. So this tg is called the growth time. Okay, so the definition of growth time is exactly opposite the half-life. So that means the time it takes the initial population or the initial colony to be exactly the double. Okay, so the growth time, this tg, is actually uh, so actually we should representing is the double growth time. Okay, rather than the growth time. Yeah, so the double growth time represents the time it takes the number of bacteria just to be double. So it is just the opposite of the t half. Okay, so once again numerical problems representing the bacterial growth by following these equations may appear in the exam. Okay, so now we will move to the application, now we move to the integrated rate laws of the second order kinetics. So let's start the integrated rate laws of the second order. So here the second order reactions can be of two types. That is, here case 1, you see that one type of reactant is giving the product just like first order. But here the another case is also possible. The two types of the reactants A and B can give you the product. And more importantly, like for the case 1, the same thing can be expressed in terms of the rate of disappearance of the reactant, or it can be expressed in terms of the appearance or the rate of the appearance of the product. Okay, so here also we would only represent the reaction that in terms of the appearance of the product dx dt. So you see that we have three scenarios, 1, 2 and 3. So we will take one case at a time to see the how the integrated rate laws of the second order shape up. So let's first take the example of case 1, that is A going to P, and we have to express the reaction in terms of the disappearance of the reactant. So since this is a second order reaction, we can easily write that minus dAdt is equal to K multiplied by A to the power 2, that is A square. Why we are writing that? Because we have already stated that it's a second order reaction. So therefore we have to integrate that like last time, that is minus dA over A square is equal to K dt. Okay, and then we have to integrate that using the limits. So our limits were A naught where time t is equal to 0, and here our limit was A at any time t, or at at time t is equal to t. Okay, so or the final results. Okay, the final result gives you 1 over at is equal to 1 over a naught plus kt. Okay, so this step has been done by taking consideration of a standard integral. So the standard integral is something like this, x0 to xt, and we have dx over x square, and the standard integral goes into 1 over minus xt plus 1 over x naught. Okay, so you can try the standard integral and verify that we can reach the following integrated rate law of the second order reaction. Okay, so this equation looks linear, isn't it? So can you plot 1 over at with respect to t, and can you verify that you get a straight line, and from the intercept can you find out the value of a naught? So in other words, you please try to draw an imaginary graph plot from this integrated rate law of second order equation. So here is one question for you. Can you calculate the half-life of the second order kinetics? Okay, and I'm giving you a hint that show that the half-life, whatever you are going to find out, is dependent on the initial concentration. Unlike the first order, the half-life was not dependent on the initial concentration. Okay, so it was dependent on the rate constant, but here you will see the half-life is dependent on the initial concentration. Okay, so this is the integrated rate laws in terms of disappearance of the reactant. So now we are going to frame the integrated rate law in terms of appearance of the product, or dx dt. So let's clean the board and proceed. So as we have done the same thing just a while ago for first order reaction, we will exactly repeat that for the second order reaction. So at time t is equal to 0, initial concentration was smaller case a and the concentration of product P was 0, and at time t is equal to t, this is A minus X and the concentration of product is X. So therefore we can write that dx dt, that is the rate of the formation of the product, is equal to rate constant K multiplied by A minus X whole square, because it is second order. So now we have to integrate the above equation. So dx over A minus X whole square is equal to K dt. Okay, and of course we have to integrate that plus with the constant of integration z. Okay, or if we integrate that form, the final form means with this thing we will come into 1 over A minus X, okay, is equal to kt plus z. So we have to find out the value of the z exactly the same way as before. So that means by putting at t is equal to 0, x is equal to 0. So if we put that thing, and we can find out easily that the value of z is 1 over a. So considering the value x is equal to the z is equal to 1 over a, we can now write the entire integrated rate equation for second order from this equation, and that is 1 over a minus x, okay, minus 1 over a is equal to kt. Okay, so this is the final form of the integrated rate law of second order reaction, provided we consider the rate of the formation of the product, or that is the concentration of the product P at any time t. So remember, doing this integration from here to here, we have taken the help of a standard integration or standard integral of the type, that is x to the power a dx. Okay, so this actually, if you remember, there are some standard integrals, so it gives you x to the power a plus 1 divided by a plus 1 plus c. C is the constant of integration. Here there is only one condition that is needed to be applied, that is here a not is equal to minus 1. So then only this is valid. Okay, so from this, the same thing, can we draw the graph plot? Okay, means t versus x, okay, or 1 over a minus x versus t, as you wish. And so the usual practice, what is the unit or dimension of k? Can you find out? Okay, of course you can find out from the dimension analysis of this equation or this equation, whatever. Okay, so now we have done with the situation number 1 and situation number 2. So now we are going to get the integrated rate laws for the case 2. So the case 2 was the two different types of reactants, that means A and B, are reacting to give you the product P. So let's find out how to get a general integrated rate laws of that kind of equation. So now we come to A plus B giving you the product P type of reaction. So here, as I told you, that we are going to study this reaction in terms of dx dt. So the usual practice, that at time t is equal to 0, so this is A, this is B, and this was 0, and at time t is equal to t, we have A minus x, here B minus x, and this is x. So therefore we can write that dx dt is equal to k multiplied by A minus x into B minus x. So this is a second order reaction, so each of the concentration term individually would be dependent on to the power of 1. Okay, so like the usual practice, we have to integrate this expression k dt. Okay, so of course, so we integrate that with the constant of integration z, and so we are going to write down the expression for this one. Okay, so how to integrate this equation? So once again, we have to take the help of a standard method. That means the method of partial fraction. Okay, so if we are not familiar about the method of partial fractions, so we can review this topic once again during some of the tutorial classes or help session. So anyway, to cut down the time, we can directly consider the result of this method of partial fraction, and assuming that we have successfully integrated this equation, so therefore it gives you 1 over a minus b natural log of a minus x divided by b minus x, okay, is equal to kt plus z. Okay, so now the thing is, once again we have to find out the value of the z. So the value of z would be that once again at time t is equal to 0, x is equal to 0, and that gives me z is equal to 1 over a minus b multiplied by natural log of a by b. So if we put that value of z over here and reorganize the equation, so I have to erase this part. So therefore the integrated second order rate law, so the integrated rate law for second order would become something like this: kt is equal to 1 over a minus b natural log of, okay, so b multiplied by a minus x divided by a multiplied by b minus x. Okay, so this is the final form that we can write. And of course, sometimes we can get rid of the natural log, and we can write in a more standard form, that is 2.303 divided by a minus b log to the base 10 of b multiplied by a minus x over a multiplied by b minus x. So this is this can be treated a standard general expression for the second order kinetics. Okay, that means this is the integrated rate law. So the question is, can you plot this part, that means log to the base 10 of b of a minus x divided by a multiplied b minus x, with respect to time t. Okay, so t versus this entire expression, can you plot that? And if you plot that, what should be the slope of the plot, and how the graph plot would look like? Okay, so anyway, this is a long expression, okay, and you may like to remember it, but just make sure that you might be asked to derive this expression, okay, for solving any numerical problems. Okay, so you better know that how to solve this kind of integrated rate laws. So not only second order, first order, zero order, second order, different types, you should be familiar on how to derive such kind of expressions by taking the help of the standard integral. So next we deal with the examples of the second order reaction. Okay, so one of the examples that we have already uh, dealt with, that is, you remember that we have dealt that 2Hi is giving to H2 plus I2. So these are all gas molecules. Okay, so the dissociation of hydrogen iodide into gaseous hydrogen and gaseous iodine is actually an example of the second order reaction. And another reaction, second order reaction, is the ester hydrolysis. Okay, so ester hydrolysis of ethyl acetate. Okay, so I'm writing it in short form. Okay, so actually let's write it this way better. So C2H5, okay, just a moment. So CH3COO C2H5, and this, when this undergoes basic hydrolysis, that means the hydrolysis of ester in basic medium, obviously it gives you sorry, so it gives you ethyl acetate plus the ethanol. Okay, so this basic hydrolysis is actually an classical example of a second order chemical reaction. Okay, so after second order, automatically what comes next is a third order reaction. But however, in chemistry, the third order reactions are relatively less common, or better I would say it is rare. But in anyway, let's just review by not going into the details, a few glimpses on how to frame the rate law for the third order reaction. As I told you, that the third order reaction is relatively very rare compared to first and second order and other fractional order reaction. The reason is, anyway, let's first try to see a natural example that comes to our mind. The third order means three different reactants probably are colliding in a single step at the same time to give you the product P. But the answer is hardly any kind of such reaction is known. So that means it is very difficult to get three different types of reactants to collide at the same time. So statistically it's a highly improbable phenomenon. Rather, there are few, this type of reaction is known, and actually there are practical examples, that is A and B going to give you the product P. And since it is third order, means for such type of reaction should happen in a single step, because we are talking about the molecularity 3, and by taking two reactant means one of the reactants molecularity should be 2. So let's take the example of 2A plus B going to give you the product P. So now the question is, can we write the basic rate equation, that means the differential equation, can we frame that for dx dt? Okay, so now here there is a little catch, because the majority of the students make a mistake while try to write the expression, because there is a factor 2. So now, since we have taken the stoichiometric coefficient here, we have to consider that, or include that stoichiometric correction into the expression of dx dt. So that means it should be rate constant multiplied by a minus 2, so x, needless to say the initial concentration of A was A and B was B, and so this is 2 means it has to be squared multiplied by b minus x. So therefore if someone just integrates this equation, of course using the standard integral, he or she would be able to frame the integrated rate law for the third order reaction to understand that how x is related with any time t, provided the initial concentrations and the rate constant is known, or vice versa. So as I told you, there are a few real life examples. So one of the examples that I'm going to give you is probably this, that nitric oxide gas plus oxygen, okay, it gives you, so we have 2NO2, so it gives you the nitrogen dioxide gas. This is a readily formed reaction, okay, it means a spontaneous reaction. And another one is this, okay, so it gives you a compound NOCl, okay, or the nitrosyl chloride, it is known. So once again it's a single step gaseous reaction, okay. So what we have now, what's important is that you see reacting 3 molecules in one single step, it involves the gas phase reaction. So you see all the examples contained the molecules in gas phase. So now we have almost completed all the standard order reactions integrated rate laws, but still one interesting example is remaining, and that is called the pseudo first order reaction. So now we are going to take a look at that. Okay, so before we proceed to the pseudo first order reaction, I just realized that I made a mistake while mentioning the example of the second order reaction. The correct reaction should be just the otherwise. Probably I have written the reverse reaction, but it should be gaseous hydrogen plus iodine is giving hydrogen iodide molecule. So it's an example of the second order reaction. So anyway, let's quickly discuss the pseudo first order reaction. Okay, so the example of such type of reaction typically involves water-based reaction. That means the hydrolysis of ester. So let's take an example, that is the ethyl acetate. Okay, so when it is being hydrolyzed in water, sometimes with a catalytic amount of acid also, so then it forms basically acetic acid plus ethanol. Okay, so if we look at that, now this is a truly second order reaction because it takes 2 molecules one single step, ethyl acetate and water, to give you the product. So we can say that at any time t, the concentration is A minus X for the ester, and for water it is B minus X, etc. Okay, but the only one problem is here the water, it is present in huge excess, and at the end of the reaction basically there is practically no change in the concentration of water because it is present in such a huge excess with respect to the initial concentration of the ester, that is A. So that means here we can write that the B is much greater than equal to A. It is so big that we can write that this B minus X actually becomes is equal to B, and also the factor A minus B basically becomes minus B. So why we are writing that? Because if we try to frame it in terms of a pure second order reaction, so let's recollect the integrated rate law for the second order reaction. So the rate law is, if you remember, it is something like that, KT, okay, is equal to, if you remember, that is 2.303 divided by A minus B log 10 of b over a minus x divided by a minus b divided by x, isn't it? So this was the expression. So now if we put the conditions of these b minus x and a minus these two conditions, so this original second order integrated rate equation would change into, or kt is equal to 2.303, so a minus b becomes minus b log 10 of so b a minus x divided by a minus a multiplied by, this becomes simply so b minus x becomes simply b. Okay, so this becomes simply b, and this b cancel out, so therefore we can write the same equation as, or here I am writing that kt, okay, is equal to 2.303. okay, so if we take the negative sign off, so b by a log base 10 of a over a minus x. Okay, so can you see that? Anyway, so I think this since the space limitation, this expression is appearing a bit clumsy, so I'm going to erase that part and I'm going to rewrite this expression over here. Okay. Okay, so for clarity and the space problem, I have erased the board and I have rewritten the derivation for the expression of pseudo first order reaction. So our condition was b minus x was b and a minus b is equal to minus b. And this was the original expression for the second order integrated rate law. So if we put those two conditions over here, so a minus b becomes minus b and those b cancels out, we have this. And to incorporate this negative sign, we have flipped this fraction over here, so it becomes kt is equal to something like this, and then therefore we can shift the b over this part. So as you see, the kb is equal to this expression, and the b is the initial concentration of water, which is essentially a constant. So we have the new constant k prime is equal to 2.303 divided by t multiplied log base 10 of a divided by a minus x. Now you see this part is already resembles the first order chemical kinetics. So that's why this is called the pseudo first order integrated rate equations. So the k prime is the new rate constant. So here in this type of reaction, the pseudo first order, one thing we must remember, that is, although the rate is rate constant multiplied by water multiplied by the concentration of S star, since H2O is constant, okay, so we can readily include the initial concentration of water within the rate constant, so it becomes k prime multiplied by the concentration of S star. So here k prime is your new rate constant, or we can call it the rate constant of the pseudo first order reaction. Okay, so and there are many examples, practical examples. We will later see that how this equation for the pseudo first order reaction will help us. Okay, so now we will move on to some basic methods of determining the order and rate constant of some unknown chemical reaction. Okay, so there are few methods for determination of order and rate law simultaneously. So the first method that we are going to learn today is the method of integration. So this is also known as the trial and error method or the graphical method. So in this method, what happens basically that we collect a series of AT versus T data. Okay, and remember in this method we basically record or follow the reaction in terms of the disappearance of the reactant. So that means we measure the amount of reactant left at any time t, which is AT, and then we try to plot the graph of AT versus T by matching it one of these standard formats. So for example, so if the graph plot is taken AT versus T, and if the outcome is linear, then we call the order is 0. Okay, and likewise if we plot 1 over or if we plot the graph plot of natural log of AT versus T, and if that graph plot comes out to be linear, and we call the order is the first order. Or if that happens to be the graph plot that 1 over A versus 1 over AT versus time t happens to be linear, then the reaction becomes the second order, or it follows the second order rate law. So from this thing we can find out the order n, whether 0 first and second, and likewise we determine the rate laws. So this is purely a trial and error method. So it depends on the best fit. So whether AT versus T, the data gives you straight line, or whether natural log of AT versus T gives you the straight line. So the accuracy, that means the measurement of the order, the accuracy would be very much dependent on the type of the best fit that you are going to consider. Okay, and not only that, what happens if the reaction is of the fractional order? So for these two reasons, this method of integration or trial and error method works best when your reaction is of purely 0 first or second order. So for other types like the fractional order, this method fails. But indeed, sometimes for some simple 0 first or second order reaction, this method is useful. So next we try to learn another method that gives us a general way to find out any type of n, be it 0 first, second, or fractional. So let's discuss that. So now let's discuss the second method. It is called the differential method or Van 't Hoff's method. So this method is practical, and a large number of chemical reactions is followed in terms of this differential method. So here what we can write, that is the rate that is minus dA dt, that means the rate of the disappearance of the reactant, is here we can represent this as dC dt. Okay, so of course here A is equal to C is equal to rate constant multiplied by C to the power n, and this n is unknown because we don't know what is the n. We are going to determine the value of n. So here what we do basically, that we run the reaction with two different initial concentrations. Okay, so for example we start with some initial concentration C1 and some initial concentration C2. So if we do so, then we can write the above equation with a different dC1 dt is equal to k C1 to the power n, and also minus dC2 dt is equal to k C2 to the power n. Okay, so here C1 C2 represents that this reaction has been the reaction is being done with two different initial concentrations. Okay, so as you can see that why we are writing dC1 dC1 dt and dC2 dt. Of course this differential means this expression has a meaning, has a particular significance. We will come to that later on, but let's try to discuss that how n is typically found out. So once we have written that, so what we actually do is, or we take the log values. Okay, So that means we take the logarithms of both left and right hand side. So I'm taking the log values over here. So or log to the base 10 of this part is equal to, we can write log to the power base 10 of k plus n log C1. Okay, so we can call it our equation 1. Okay, and similarly we can frame the equation 2 here. So log to the base of dc2 dt is equal to, once again, log base k plus n log c2. So this is our equation 2. So now we have got these two equations, and from here we try to solve the value for n. So what we do, that we subtract the equation 2 from equation 1. So if we do so, we can express the value of n is equal to log 10 of minus dc1 dt, okay, minus log minus dc2 dt, okay, and then it divided by log c1 minus log c2, isn't it? So therefore we have a pretty long expression, and we can easily measure n provided we know c1 and c2. Those are the two initial concentration. So you may argue that C1, C2, the initial concentrations, mean it should be constant. Then how come we take minus dC1 dt here and minus dC2 dt here? So that's what exactly I'm going to discuss now. Okay. So the question is how to find this dC1 dt and minus dC2 dt. So what are those two derivatives mean? Okay, so these two derivatives mean that these are representing two different initial rates, because this dc1 dt and dc2 dt are actually, they represent the slope of c versus t plot. So we can write that dc dt is nothing but the slope of c versus t plot at any time, at any point. But if we consider the c versus t plot from a non-zero order reaction, okay, c versus t, you remember it falls like this. So the slope is being changed at every point here. So if the slope is changing at every point, then how come we determine dc dt? Okay, so for that we have to take some approximation, and that approximation is known as the initial rate. So what's that approximation? So let's erase the board and let's draw a graph plot, and from that it would be clearer to us. Here I have drawn a graph plot of C versus T. So this is the time axis and this is the concentration axis. So we have started the reaction with two different initial concentrations, C1 and C2, where C1 is greater than C2. So if C1 is, if we start the reaction with a higher concentration, so obviously the its fall would be steeper. Okay, that means this curve, so the decay curve would be something like this, and for the lower concentration the curve is somewhat flatter. Okay, because the rate depends on the initial concentration. So if initial concentration is smaller, the rate is lower. So now the thing is, this minus dc1 dt, this derivative is only meaningful when t tends to 0. So when t tends to 0, so that slope is actually at this point, and we can draw this straight line. So this is basically nothing but minus dc1 dt when t tends to 0. And so therefore this is called, this minus dc1 dt is the initial rate. Okay, and for this one, you see at the very beginning when t tends to 0, if we try to draw the slope, that is minus dc to dt, okay, the negative slope at time t is equal to 0 or time t tends to 0, this slope is flatter than this slope. Okay, so therefore the initial rate of this one is slower than this one. So the approximation is we have to measure the two initial rates at the very initial stage, that means when t tends to 0, that means at the very beginning. So this is an approximation method, and so this approximation is holds true up to maximum 10% of the entire reaction. So that means we can assume that whenever a reaction starts, okay, it would definitely fall down exponentially, but for a very limited amount of time at the beginning, that the time period is very small, the fall, that means the decay, would appear as if it is a straight line. Okay, and that approximation can be taken up to first at the most maximum 10% of the entire reaction time. So if I want to measure the initial rate, the fastest we can measure it is the better. That means if the reaction is spans for total 10 minutes, so we have to measure the reaction within first 1 minute, or better within first 10 or 20 seconds. Okay, so this is how it explains. So once we measure this dc1 dt and dc2 dt, the formula that I have written earlier, from there we can easily find out the order. Okay, and this is called the Van 't Hoff's differential method. So we stop it here today. So in the next lecture we would continue with our third method, okay, and so on. So I will share also some of these lectures in terms of PowerPoint slides with you, and also I will mention the textbook. So you please follow these video lectures, the lecture slides and the textbook to study these preliminary parts of the chemical kinetics. Okay, so I will see you in the next lecture. Stay put and stay safe. So till then, goodbye.